Okay, so I want to start by talking about something that I should have mentioned yesterday. So we've been talking about holomorphic functions of several complex variables, and then one thing one should mention is sort of the right definition of meromorphic functions of several complex variables. So, you know, like even in one complex variable in basic complex analysis, a holomorphic function can have a bunch of isolated singularities, and then you classify the singularities. They're either removable if the function extends holomorphically, or so then the worst kind of singularities are the essential singularities where there's something transcendental going on, like e to the 1 over z. And then sort of in the middle you have the singularities of meromorphic functions where the thing blows up at worst polynomially as you approach the singularity. And so the right way of generalizing this definition to higher complex dimensions is to say that the function is meromorphic if it can be locally written as a quotient of two holomorphic functions. Then you see sort of the singular set of the function, which is like the locus where the denominator vanishes, is not just going to be a single point anymore. That's what we were talking about last time. So it's going to be some kind of complex submanifold or some sort of analytic subset. So the function isn't actually well defined on a whole analytic subset, and that's kind of awkward to sort of formalize. So then the best way of saying what a meromorphic function of several complex variables is I mean, sort of not to try and put that intuition into words, but do something slightly looks strange, but it's actually the sort of the better way ultimately. So we're saying that a meromorphic function on an open set U in Cn consists of the following data. So it's not actually by definition a function. So of an open cover of my domain. So I'm going to write my domain as a union of open subsets in some arbitrary index set. And then for each index, I want to take a pair f alpha, g alpha of holomorphic functions on that open set. So f is going to be the numerator and g is going to be the denominator. So g alpha not identically 0. Such that f alpha g beta is equal to f beta g alpha for all pairs of indices alpha beta on I guess u alpha intersected u beta. So that's just saying that the ratio f alpha by g alpha is the same thing as the ratio f beta by g beta whenever both ratios are actually defined. So it's something that's locally a quotient of two holomorphic functions. And exactly what holomorphic functions I have to take can vary from patch to patch. And I don't want to actually call this a function because it can have singularities, and the singular set, which is locally the zero set of the denominator, can have some sort of complicated structure. So this is sort of, and you can see the monster of sheaf theory rearing its head. So that's a sheaf theoretic definition. Hope I won't have to talk about sheaf theory anymore. So that's just a definition, and I want to give you one basic example that really shows you what's going on in higher complex dimensions. So where higher complex dimensions are really different from a single complex variable. So it's a basic example, and that's really fundamental. So the function f of CW equals Z over W on C2. So you have the complex coordinate axis in C2. This is W equal to 0. That's what you would call the pole set of F. So when you're dividing by 0, and then here you have Z equal to 0, it's a 0 set of F. So far, so good. What's really new in several complex variables is that the two can intersect. So there's points of indeterminacy where the expression doesn't even make sense. And that's not just some nasty kind of pathology, but that's really a fundamental phenomenon in several complex variables. And there's going to be an exercise on the homework sheet of inviting you to think more carefully about what's going on. So so this phenomenon necessitates of introducing the technique of blowing up. So you want to resolve the indeterminacies of meromorphic functions. And there's a technique for doing that. It's called blowing up, and it's sort of fundamental to a theory of complex surfaces and complex manifolds in higher dimensions. And that shows up in other sort of areas of geometry as well. Sort of resolving singularities by blowing up. That's going to be in the homework, and we'll discuss blow-ups later on anyway. Okay, so that's that. So, sure.
So, what is the notion of two meromorphic functions being equal?
Yeah, I guess if they're equal wherever the quotient is actually defined. Yeah. Sure. I mean, you have an equivalence relation, right? You could alter each pair by multiplying both components by the same non-vanishing holomorphic functions.
Like the equivalence relation of the pairs. What exactly is the equivalence relation for the covers?
I guess you want to have a common refinement of the two covers. Say that again? I didn't get that. Oh, yeah.
So you just combine the two data, and then if there's still...
Okay, people are nodding. It's still in. It's a good thing.
You just take the
Yeah.
union of both.
Yeah.
Like two things are the same when you take the union and define another.
Okay, I think that's right. Yeah.
We simply define by a function that holomorphically map to the Riemann speed.
No,
One.
that's true in complex dimension 1.
Only one.
Yeah. Because the correct statement is that, so for example, like here at the point of indeterminacy, you don't actually have a map to anything. I mean, sort of on the 0 set, no question, the thing is just 0, like if I exclude the origin. On the pole set, if I exclude the origin, the value is just going to be infinity. So I can just go to the Riemann sphere and, map to the point at infinity. But at the point of indeterminacy, in some sense, the function becomes multi-valued. So if the set of values becomes the whole Riemann sphere. So if you want to get rid of that, what you have to do is you have to blow up the point of indeterminacy, meaning you're going to replace it by a copy of the Riemann sphere. And then you can pull this thing back. You can pull your function back to the blow up. And then it's going to give you a well-defined map to the Riemann sphere. So like a meromorphic function is like a holomorphic map to the Riemann sphere, but on a different domain. And the domain is going to be a blow up of the original domain. Except that blowing up is a trivial process in complex dimension 1. So that's something that only exists in complex dimension 2 entire.
Is this blow-up procedure at all canonical?
Yes. Yes. Right. I mean, so the basic problem is that the function takes sort of. I mean, if you approach the origin, on a line, then this function is going to be constant on that line. So it's going to be taking different values depending on what directions you approach the origin in. The space of directions of lines through the origin in C2 is a Riemann sphere. Okay. That's actually probably the most interesting thing I prepared for today. So I wanted to go through the definition and some basic examples of complex manifolds, but that's going to mirror Jacob's lecture to some non-trivial extent. But I'm going to try to at least make some different points or emphasize some different points. So I'll be quick on the definitions and spend some more time on the examples. So we want to define notion of complex manifold. Mn. So I'm just going to say that you take the definition of a real manifold, of a smooth manifold, and you replace, diffeomorphisms between open sets in Rn, which is what the transition functions are by definition, by biholomorphisms between open sets in Cn. So smooth manifold. With holomorphic diffeos. So otherwise known as biholomorphisms. It's a term that Jacob used. Biholomorphisms. But if you have a diffeomorphism, which is actually holomorphic, then the inverse diffeomorphism is automatically going to be holomorphic as well, because holomorphy just means that the differential or Jacobian matrix is complex linear. And if that's true, then the inverse of Jacobian is complex linear automatically. Right, so then you have complex submanifolds. So for n, so presuming that Mn is already a complex manifold, and you want to say what it means for Nk to be a complex submanifold, and then you just, it's a real smooth submanifold in the ordinary sense. So that's of the local flattening map, like that makes the thing locally equal to chunk of Euclidean K space is actually a holomorphic map. Um, Terminology, when n is equal to 1, then M is a complex curve or Riemann surface. That's what we already know. And the only reason I'm mentioning this again is that when n equals 2, people usually call a two-dimensional complex manifold a complex surface. To be some confusion between Riemann surfaces and complex surfaces. So I guess one more boring definition. So holomorphic map. So you have a smooth map. Between complex manifolds is holomorphic. If F is holomorphic, if you express it in local holomorphic charts for the two manifolds. We have the slightly nicer definition that that's actually equivalent to the differential being complex linear everywhere. Right, so we, on each of the tangent spaces of a complex manifold, we have a well-defined notion of what it means to multiply by I, because we have that on Cn, and the transition functions are holomorphic, so they're preserving, the differentials are preserving the notion of multiplication by I, so that makes sense. So it's something that commutes with multiplication by I, linear map. And then just one remark in a similar spirit, that this whole business of PQ forms introduced last time, so for the exact same reason actually generalizes from domains in Cn to complex manifolds. So if the notion of PQ form, a form of being of type PQ, is invariant under biholomorphic maps, so therefore just immediately generalizes from domains to manifolds. On a complex manifold. We have a notion of a differential K form. K between 0 and 2n, the real dimension being of type PQ. So we're P plus Q equals K and P and Q most n. Okay, so then we have the operators del and del bar in the same way. It just globalizes from domains to manifolds. So we from lambda PQM lambda P plus 1 QM to lambda P Q plus 1 M stel bar. And D decomposes as del plus del bar. I think we're never actually going to have to use this except when P equals Q equals 1. So 1-1 forms are the most interesting ones for us. Okay. And the rest of the lecture is just going to be like a list of basic examples, sort of similar to what Jacob did, but I'm going to be mentioning some more properties without proof. So I have made a list of 5 groups of examples. And the first 2 groups are sort of going to be the extreme cases in a way. So that's affine and projective manifolds, so things that live in affine space and things that live in projective space. So we have affine space. Cn plus 1. And then we have affine manifolds. Some people would say Stein manifolds. And of course, depending on who you talk to, that's either a definition of Stein manifold or a theorem. So that's Mn, M inside C. Just stick with Cn, a closed complex submanifold. Yeah, so for example, the zero locus of polynomial without, away from the, if the polynomial has no critical points, then complex critical points, then zero locus is going to be closed complex submanifold. So that's the complex manifolds that can be embedded into affine space, that exist as submanifolds of affine space. Now, if you want, that's for one of the main differences between smooth manifolds and complex manifolds. That every smooth manifold can be smoothly embedded into affine space of sufficiently high dimension. That's the Whitney embedding theorem. But nothing like that is true for complex manifolds. So affine manifolds or Stein manifolds are extremely special in various ways. And the first way in which they're special, that's Jacob's homework problem, is that they're either points or non-compact, assuming they're connected. M connected affine. M is a point, or not compact. So like Jacob said, there's many ways of proving something like this. It's a PDE argument, right? It's an argument about, well, there's a pointwise way of proving that by using the maximum principle, and there's sort of slightly nicer way that I prefer by using, an integral identity. That's, so affine space doesn't contain any compact complex submanifolds. second fact is that every non-compact Riemann surface is actually Stein or affine, and you can actually embed it into C3. So every open Riemann surface. Embeds holomorphically into C3. And that's a little bit like the Whitney embedding theorem, because 3 is 2 times 1 plus 1. Another fact, I mean, these results are extremely, I mean, the first one is easy, that's a homework problem. This one is, that's a difficult theorem, and C is going to be difficult as well. So that's a statement that, if you have a submanifold like this, it's always the zero locus of a bunch of holomorphic functions. Every M affine can be written as possibly you need many more functions here than the codimension of M would make you think. So you might need many more functions than n minus the dimension of M to achieve this. So if we say that M is algebraic if these functions can be taken to be polynomials. So the last fact is something that I was trying to get you to prove as part of the homework yesterday, which is that affine manifolds are minimal surfaces in Euclidean space necessarily. Affine manifolds. So in the sense of minimal surface theory, that there are critical points for the volume functional. So if you take an affine manifold, take this non-compact thing, you perturb it locally, then no matter what perturbation you take, it's going to be a critical point for the area functional. And actually much more is true, they're going to be global minimizers. So if you take an affine manifold and perturb it locally, then the area can only, the k-dimensional volume or 2k-dimensional volume can only increase. So global area minimizers in the homology class. And again, so this is something that's basically a homework problem too. So it's first noted by Wirtinger in the 20s or 30s, I think, and then Harvey and Lawson went ahead and sort of invented the theory of calibrated geometry as a generalization of that fact. So there's a beautiful, simple argument that lets you prove that. And in particular, this means that just by looking at the zero locus of a bunch of polynomials, you can create submanifolds with singularities, possibly, that are absolute area minimizers. So there are examples and counterexamples of in the regularity theory of minimal surfaces. So in particular, they show that if you're looking at area minimizing submanifolds whose real codimension is at least 2, so which are not real hypersurfaces, and sort of codimension 2 singularities are unavoidable. So you don't have this codimension 7 singularity statement like for minimal hypersurfaces. Okay. So then next up is the extreme opposite, projective space and submanifolds of projective space. Just going to try and say something that Jacob didn't already say, and there's not that much left. So anyway, so we have projective space. So CPN. I'm usually going to write that as PN. And projective manifold, so it's closed complex submanifolds of projective space. Right. So the best definition is to say that this is a quotient space, the space of lines with the origin in Cn plus 1. So it's a quotient. I'm taking Cn plus 1 minus the origin, and I'm modding out by the action of the multiplicative group of non-zero complex scalars. So identifying two complex vectors if and only if they span the complex line. In other words, if they differ by multiplication by a non-zero complex scalar. So modding out by C minus the origin. So now, on one hand, you can use this to see that Pn is compact, because you're just doing polar coordinates, right? You have a radial direction and sort of a polar direction, a polar angle direction, so r and theta. And I can just throw away the r part on both sides. So I have an r and a theta on both the numerator and the denominator. I can just throw out the r. So what remains is the theta, sort of in a non-trivial way. So this is actually then going to be the quotient S2n minus 1. So the unit sphere, S2n plus 1, the unit sphere in Cn plus 1, modded out by the action of the group of unit complex scalars. So the orbits of that action on the sphere are called the Hopf circles, and the quotient map to CPn is the Hopf map. So that immediately tells me that projective space is compact. It's a quotient of a compact space. So there's one other thing that this formula is good for. It tells us a lot about the structure of projective space. So I'm going to expand this as a geometric series. Okay, so this is all you need to know about the structure, the topological structure of projective space. Tells you everything. Okay, so what does this mean? well, Jacob basically already said it. So I have this covering of projective space by affine charts. So I have n+1 affine charts, and each of them is isomorphic to a copy of Cn. And so of homogeneous coordinates. C0, C1, Cn. So it's just the equivalence class of the corresponding vector under multiplication by non-zero scalars. And then my affine chart, Ui, that's the locus where coordinate Ci is not 0. That's actually isomorphic to Cn. Well, yeah, I'm sending this homogeneous vector to C0 Ci, C1 Zi. I'm going to leave out Ci, Zi. Cn by Zi. Taking these ratios that are well defined. Another point is the complement of this affine chart is actually projective space in one dimension less. Right, so Pn minus this chart Ui. So this is a set of all homogeneous coordinate vectors where the ith coordinate is actually equal to 0, just by definition. And that's sort of visibly isomorphic to projective space in one dimension less. And then you see that you can understand the structure of projective space inductively. You have a copy of Cn and a Pn minus 1. The Pn minus 1 contains a copy of Cn minus 1 and the Pn minus 2, and so on. So that's what this formula is saying. So that gives you actually a cell decomposition or CW composition of projective space that lets you compute the Betti numbers and the homology groups and the fundamental group and all that stuff sort of by inducting on the dimension. So, for example, projective space is simply connected in every dimension. That's, if you have this picture, then that's it's an application of the Van Kampen's theorem, sort of inductively. Pi1, Pn is 0, and I guess you can compute that. You can compute the integral homology and cohomology. I'm just going to write down hi of Pn. So this is going to be copy of the integers if I is at most 2n and even, and it's 0 otherwise. Projective space has homology only in even degrees corresponding to the projective subspaces. I mean, the cycle is represented by the projective subspaces of the corresponding dimensions. Another list of facts. So every projective manifold can actually be written as the zero locus of a bunch of polynomials. So this is sort of similar to what I said about affine manifolds, except that the defining functions are now actually going to be homogeneous polynomials always, and nothing else. Cn plus 1 to C is a homogeneous polynomial. This means every complex submanifold of projective space is automatically algebraic. It's given by polynomials and not just by holomorphic functions. So that's Chow's theorem. So this distinction between algebraic and transcendental doesn't exist for projective manifolds. Same way that it would for affine manifolds or holomorphic functions on affine space. In fact, every compact Riemann surface embeds into P3. So in particular, every compact Riemann surface is actually algebraic. So this, one way of proving this is to use the Kodaira embedding theorem, and I hope to tell you a little bit about that in the last lecture this week. Yep. No. It's you might need many more polynomials than sort of indicated by the codimension, because if you take only codimension many polynomials, then your zero set might still contain other components that don't belong to the variety that you want to cut out. So other components of the same dimension, and then you need to add extra conditions to remove those guys. So one other remark I'm going to make here is that so the algebraic curves in CP2 that Jacob was talking about don't exhaust the class of all possible Riemann surfaces. So every Riemann surface maps into P3, but not necessarily into P2. That's a beautiful topological argument. That's probably going to be a homework problem at some point. But not into P2 in general. And so the fact that you can prove is that if you take the zero set of So if you take the zero set f equal to 0 in P2, where f is a degree d homogeneous polynomial on C3, if that's your Riemann surface M, then the genus of M, so M is going to be a compact orientable surface, so it's characterized by its genus. And there's something called the degree genus formula that tells you that the genus of M is 1/2 times d minus 1 times d minus 2. Not every integer is of this form, so not every compact Riemann surface maps into P2, but they all do map into P3. Yeah. So, yeah, but that's not an embedding. That's like an immersion into P2. That's right. So it can always embed into P3 and immerse into P2 if I allow some sort of double points where the surface is crossing itself. And C is sort of the same thing as before, sort of projective manifolds are absolutely volume minimizing in their homology class. So that's affine manifolds and projective manifolds. Third class of examples is kind of lame. I can always take products of complex manifolds that I already know. But there's sort of okay. Affine cross affine is affine. So there's nothing there. That's clear. That doesn't give me anything new. Now you want to say that the same is true in the projective category, so that product of projective manifolds is projective. And that's not so clear, actually. What you need to show is that if you take a product of any two complex projective spaces of any two dimensions, then that actually embeds into some higher dimensional projective space as a submanifold. And that's not obvious. And so on the homework, there's going to be one exercise where you can check that in the lowest possible non-trivial dimension. So that's a very good exercise, I think. This is not so obvious, actually. And then sort of clearly affine cross projective is neither affine nor projective. Unless one of them is a point or something like that. Because if neither of them is a point, then it contains compact complex submanifolds from the projective factor, so it can't be affine, and it's non-compact from the affine factor, so it can't be projective. So there's sort of mixed cases in between. So I have two classes of examples left, but I'll probably only do the first one. So it's free quotients. So you have M, a complex manifold, and gamma, a subgroup of the complex automorphism group of M, so of the group of all biholomorphic self-maps of M. Acting freely, properly discontinuously, whatever, on M, freely and discretely on M. That's just the conditions that you need in order to turn the quotient M mod gamma into a smooth manifold. And then it's automatically going to be a complex manifold because, by assumption, gamma is a subgroup of the biholomorphism group of M. So it's going to preserve the complex structure, and the complex structure is automatically going to pass down to the topological quotient. So first example is a non-example. You might ask, what if I start with Pn? Can I find a discrete subgroup of the automorphism group of Pn that acts freely so that the quotient is going to be a complex manifold? And that's not possible. So the automorphism group of Pn, pretty much the same as for the Riemann sphere, so you can show that this is PGL n plus 1 C. So it's the maps that are induced by linear maps of the n plus 1 dimensional affine space. And every element of PGL n plus 1 C has fixed points on projective space. So a group like this, a finite subgroup, can never act freely. And well, the reason, there's at least two ways of seeing this. The first one is to say, well, these guys are complex matrices. Complex matrices have eigenvectors, at least one eigenvector. If it's an eigenvector, then it reproduces itself up to a scalar, so it means it defines the same complex line, so it's a fixed point on projective space. And so the better way to see this is to use the Lefschetz fixed point theorem. You compute the homology groups of projective space, and then at least when n is even or something, Lefschetz tells you that there have to be fixed points. And if you want to get n odd as well, then you need a holomorphic Lefschetz fixed point formula of Atiyah and Bott. So every holomorphic transformation of Pn has to have fixed points, so there are no free quotients. So then affine space is more interesting. So I'll make another digression here. What's the automorphism group of affine n space? So Jacob mentioned that when n is equal to 1, this is just a group of affine linear transformations. It's just Z goes to AZ plus B if n is equal to 1. Now what I'm going to say next is not important for constructing interesting quotients at all, but it's kind of surprising to see that when the dimension is at least 2, you can have much more complicated automorphisms. Every linear map is going to be an automorphism, every complex linear map, but you have much more complicated things. For example, if you take in 2 dimensions, you could do something like ZW goes to ZW plus f of Z, where f is any holomorphic function on C. So it's almost obvious that that thing is a biholomorphism of C2. So the automorphism group of C2 is infinite dimensional. It's actually known exactly what the automorphism group of C2 is. And when n is at least 3, then the automorphism group of Cn is not actually known. That's sort of one of the big open problems in algebraic geometry. And even if you restrict to algebraic functions, if you take f to be a polynomial, clearly you still get an infinite dimensional space of automorphisms. You don't even need transcendental functions here. So when n is at least 3, then it's, I think when n is equal to 2, then it's known that all automorphisms can be generated. I'm not sure if that's literally right, but I think all automorphisms can be generated by linear maps. And these guys, and in dimension at least 3, that's not known. Well, I think it's known that there are even worse automorphisms than this, but nobody knows what all of them are. That's just sort of curiosity. It's not really important sort of for the nice examples that I want to talk about. So you have obvious groups that you can mod out by. So that's just discrete groups of translations, or V1 through Vn are vectors. And if these guys are linearly independent, so if they span the whole space, then your group is what you would call a lattice, and the quotient is actually compact, and so that's a complex torus. So if these guys are a basis of Cn, then gamma is a lattice. Cn mod gamma is compact. We call it complex torus. I mean, topologically, they're all the same, right? They're a product of 2n circles. So they're all diffeomorphic to S1 to the 2n. But the complex structures are really genuinely different. So if I change the lattice, I really get a completely different complex manifold. And in general, most of them are not going to be projective. Just some of them will be. So it's a nice thing you can try to prove. Just give you the criterion for when two complex tori are isomorphic. So if Cn mod gamma is equivalent to Cn mod gamma tilde, if and only if there exists a matrix in invertible complex n by n matrix that maps the first lattice to the second lattice. So that's not too hard to see. So what you have to do is you lift to the universal cover. So you have Cn mod gamma. You have Cn mod gamma tilde. You assume that you have some automorphism, some isomorphism F between them. Then this is the universal covering map. So you can certainly go like this. Universal covering map here. Now Cn is simply connected, so you get a lift. And that's a holomorphic map from Cn to Cn, actually an automorphism. You might say, it's horrible, we don't actually know what the automorphisms of Cn are in general, except when n is equal to 1, so we can't really say what F tilde is. But that's it's not really a problem, of course, because F tilde is going to be equivariant with respect to the actions of the deck transformation groups. So this means that F tilde is going to have linear growth. Has linear growth by equivariance. And then I can just use Liouville's theorem to say, it's given by a bunch of holomorphic functions of adverse linear growth. So all the component functions of F tilde have to be linear polynomials, and then has to be invertible. So up to choosing a base point in the universal covers actually has to be a complex matrix. That's what you would do if the V1 through Vn were the standard basis of Cn. So if I take the standard basis of Cn, then this just means I identify points whose coordinates differ by integers.
And when n is equal to 1, then your gamma would be just z?
Thank you. So what did I do here? So I actually need a real basis for Cn. I'm sorry. Thanks. That's a good point. So V2n. That's a very good point. Okay. Thanks. That's great. Just make one final remark about tori. So now we know that there's sort of lots of different tori. The remark is that most tori, so these are compact complex manifolds, and they're actually Kähler manifolds in an obvious way. So it's very nice Riemannian metrics. So from the point of view of analysis, they're as simple as a complex manifold can be, but most of them are actually not algebraic, so most of them cannot be embedded into projective space. So most tori are not algebraic, are not projective. Unless n is equal to 1, so then we're talking about Riemann surfaces. All Riemann surfaces are projective, and a Riemann surface with underlying topological surface is a torus, is called the elliptic curve. As Jacob mentioned, those are always given by cubic polynomials in CP2. So that follows from the degree genus formula that I wrote down. The degree of the polynomial is 3, then the genus is going to be 1. So the thing is a torus. And there's sort of a normal form, w squared equals z times c plus 1 times c plus t, where t and c is a parameter. So you have a parameter t and c, then you write down this polynomials in two complex variables z and w. That's going to give you an affine curve in C2. You can pass to the projective closure in CP2. It's going to be given by a cubic homogeneous polynomial. And this one parameter family exhausts all possible isomorphism types of elliptic curves. So each, up to isomorphism, each elliptic curve occurs once and only once as a member of that family. Okay, that's it for today. And sorry for going over time. Next time we're actually going to prove stuff again.